Okay. Uh, Good afternoon, students. Is it able to audible my sound? Any one of you? Because somewhat some disturbance has happened now. Is it audible my voice? Anyone?
Yes, sir, it is.
Okay, okay, right. Now I'll share this whiteboard and I will start the class. So in the last class, what we have seen is we have seen about some electrostatistics we have seen, and also what we call gas law we have seen in the last class. Now we'll move to the application of the gas law. One of the application which we have to see is this uniformly charged sphere. Okay, so that will now start. So 1 minute, I'll share the. So host, please, can you enable to share this screen, share screen? It is disabled there. So please, can you enable that one? Share screening option. Please, host, please, can you enable this share screen option so that I can write my, continue my class? You're unable to get share screen here. I want to share disabled. Share screen option is disabled. Please, can you enable that one? One minute. Okay, now this is enabled. So now we'll see this. Now it is audible, no? My sound clear, no? Anyone of you should respond. Now we'll see this what we call application of this gas law. So the first application here for you, which you have is the electric field. So this uniformly uniformly charged sphere. Uniformly charged sphere. Right. So now we'll apply this Gauss law, which we have seen in the last class for this uniformly charged sphere. So here, when we are studying about electric field due to uniformly charged sphere, we are going to get three different cases we are going to be get. So we have to find out this electric field at a point outside of the charged sphere we have to find out. And similarly, second case, we have to find out this electric field at a point on the surface of this charged sphere we have to find out. Similarly, next, we have to find out the electric field at a point inside the charged sphere. So these are the three cases where we have to find out the electric field due to this charge sphere. So first one here, we will see this first case, case one. So here we'll find out this electric field at a point uh, outside of the outside the charged sphere. Outside this charged sphere, we'll find out this electric field. Okay. So in order to find out this electric field at a point outside of the charged sphere, so we will consider a sphere we are going to consider which is having some radius. So here we'll assume that radius of this sphere will be some capital R with center O we are going to be assume. So for that purpose, here we'll draw a sphere here. So here this is the sphere we are going to be draw. The center of the sphere is this one, which is O center, and the radius of this sphere is we are going to be take this as a capital R. Okay, this is the sphere which we have. So we have considered a sphere of radius capital R with a center O as which I have drawn here. Now we'll take a charge Q which is uniformly distributed over A. So here throughout this sphere, throughout this sphere, we will be considering the charge of the sphere as a Q is the charge which is distributed uniformly over the sphere we are going to be considering. Now we'll take a point P, which is outside of the sphere, which is having certain distance from the outside of the sphere. So here we will consider a point P here. Okay. So where, which is outside of the sphere, which is at a distance of, say that small r. Okay. So we have taken a point P, we have taken, which is outside of the sphere, which is located at a distance of small r from the center of the sphere, which is located. So for this purpose, at this point, we have to calculate this electric field E, we have to calculate here. So for this purpose, what we will do is, we will construct a Gaussian surface of radius smaller or OP we are going to be take, which is a concentric sphere. A is the sphere here we considered. So the sphere A we have considered. So for this purpose, we have to construct a point P where it is passing. So here we'll draw with the dotted lines around this one here. So similarly at this position like this. So this constructed Gaussian surface which is located outside of this on the point P where it is located. So here we considered a point P. Here we'll take a small surface area which is at a distance of smaller from the center of the sphere. Electric field is directed along the outward normal here. So electric field here it is directed along the outward normal. In this direction, electric field E is directed here. Okay. Now we consider a smaller surface here, smaller surface here. So this surface, we will take it as a smaller surface as a ds we are going to consider. So for a smaller surface, which is a Gaussian surface, we can call ds. So which is directed radially outward. Okay. Uh, as for the Gaussian surface. So from the Gauss law, whichever we have seen, so this will be uh, E dot ds you are going to be have, as electric field E is directed normal and ds is also radially outwards. So this will be E dot ds it is going to be have. So this E dot ds is nothing but its value is E ds cos 0, because both are in the same direction you are going to be have. So therefore it will be equals to E ds, because cos 0 is 1, so it will be E ds you are going to be have. Why we have taken this E ds cos theta cos 0? Because the angle between the E and ds is 0, because this E is in this direction, E is in this direction only, and similarly ds is also in the direction same. So both are parallel to each other. The angle between them is 0. So the angle we have considered it as a 0. Therefore, EDS cos theta, which will be equals to EDS. Now, after this one, we will calculate the electric flux through the entire Gaussian surface we have to calculate. Okay. Now, we'll take the electrical flux, otherwise electric flux, electric flux phi generally we'll call, through this entire Gaussian surface, through entire Gaussian surface, through entire Gaussian surface, which is given by, we call it as a phi E, which is a flux, electrical flux, which is equals to surface integral of E dot ds. Okay, so this is the electrical flux or electric flux through the entire Gaussian surface, which is a phi E, which we can get it as a surface integral of E dot ds we are going to be writing. So this E we can take outside, so therefore it will be surface integral of ds you are going to be have. So this will be equals to E, surface integral of ds will be equals to 4 pi r square. It will be equals to 4 pi r square. Why? Because the area of Gaussian surface of radius r is equals to 4 pi r square. So this is the Gaussian surface which we have drawn. So which is at a distance of this point, which is located at a distance of r smaller from the center of the sphere O. So that is the reason why this surface integral of ds we are getting it as a 4 pi r square. That is the area of Gaussian surface, which we have r is equals to 4 pi r square. So therefore, it will be E into 4 pi r square. Okay. So in this equation, E is nothing but it is a constant at all points, and hence we have taken out of the integral. Thus, E is taken out of the integral. Why we have taken this out of the integral means because E is constant at all points, and hence we have taken out of the integral. Now, according to Gauss law, already we have studied, the Gauss law is nothing but the total electric flux or a closed surface is equals to 1 by epsilon naught times the charge enclosed within the surface. Okay, so uh, from the Gauss law already we have seen in the last class. So Gauss law, we have like a 1 by epsilon naught times the total uh, charge which is enclosed within the surface. Total charge enclosed within the surface. Within surface which we have. So therefore, so this phi is, we have got it as a phi electrical flux, which we have got it as a E into 4 pi r square. It should be equals to the total charge which is present on the Gaussian surface is Q by epsilon naught times. So this is from Gauss law we have got. So from this, we can get E, that is the electric field at the point P, which is located outside, will be equals to 1 by 4 pi epsilon naught into Q by r square you are going to get. The units for this is Newton per coulomb you are having. So this is the electric flux, okay, with on a point which is located outside of the this sphere, uniformly charged sphere, which we have. So E is equals to 1 by 4 pi epsilon naught into Q by R square Newton per coulomb. This is what the electric flux which is located outside of the uniform charged sphere. Okay. And as I told that we have to calculate the electric field which is located at a point on the surface, we have to calculate so that we can call it as a case 2. So here we'll try calculate that case 2. So in the case 2, what we have is we have to calculate at a point, okay, at a point uh, on the surface, on the surface, that is a uniformly charged sphere on the surface we have to calculate. So when point P lies on the surface of the charge, the radius of the sphere and the radius of the Gaussian surface both are same you are going to be have. See here from this figure. So this is what we have seen now. 1 minute, I'll change this color. Okay, so here this is what we have taken the charged sphere, which is having a radius of r we have taken, and we have taken a point P, which is outside of the sphere, which is located at a distance of this r. Now, second case, what we are taking uh, at a point on the surface. At a point on the surface means, at a point on the surface means the point P whichever we have taken earlier outside of the sphere we have taken. Now this point P lies on the surface of the sphere. On the surface of the sphere means this P is on the surface you have. P is on the surface. So on the surface of the sphere means here the radius of the charged sphere is capital R, sorry, capital R, and the radius of the Gaussian surface is small r you have. So now in this case both are same. The radius of the charged sphere and the radius of the Gaussian surface which we have constructed, both are same. So therefore, in this case, the electric field intensity is given by E is equals to 1 by 4 pi epsilon naught into Q by you have like a, in place of small r, you get a capital R square. Okay, capital R square, and the units are same, that is a Newton per coulomb you are going to be have. So this E is equals to 1 by 4 pi epsilon naught into Q by R square, which is the electric field which is located on the surface of the charged sphere. So on the surface of the charged sphere, you are going to be have. Now next one, which we have to see here is case 3. So in the case 3, we have to see the when the point P, which is lying inside of the charged sphere. Now we'll see here case 3 here. So here we have to see at a point inside the charged sphere. Okay, inside the charged sphere. Here we have to see. Now, for this purpose, we shall find a electric field E at a point P, which is inside the charged sphere. Here, we'll take that point P, which is located inside at a distance of R dash. We are going to be considered here. So now we'll draw this picture of this one. So here, just you see, we will consider a, a this is the actual sphere we have considered. The center is at point O we have. This is the center which we have. And this is the charged sphere, which is having a surface charge of distributed here. Of R dash. So now we'll construct a Gaussian surface around this with the help of what we call a concentric circle only. Here, this is what we have. So, which is at a distance of, if this point P is lying at this position, otherwise here we'll take point P dash. Already we have taken point P, right? So now the distance from here to here, it is R dash we have, R dash. And this distance, the radius of the charged sphere, as we have taken previously, which is a capital R we have taken, the same we have to take here. Okay. Now, what we are doing is we are constructed a Gaussian surface inside of the charged sphere, which is uniformly distributed charge entire surface, which is at a point P. We have to calculate again. Here we have to take a smaller surface ds. We are going to be take here again. Again, the E, which is due to this charge, is in this direction. The electric field E is in this direction, and similarly, this ds is located radially outwards, right? So now the outward flux for a small portion of this Gaussian surface, we will take it as a E dot ds as we have seen. So this will be equals to EDS. Why? Because EDS cos theta you are going to be get theta is 0. That is nothing but actually otherwise I'll write here EDS cos theta cos 0 actually. So it will be equals to EDS. Cos 0 is equals to 1. So the angle between E and DS is 0. So therefore it will be equal to EDS. Now we'll see the electric flux through the Gaussian surface, the entire surface, through entire Gaussian surface here we'll see here. So for that purpose, what we have to do is we have to integrate that one again as we did in the same previous one, phi E, which will be equals to surface integral of E ds you are going to be have. So this will be E is constant entire surface. So we'll take outside. So it will be E surface integral of ds you are going to be have. So which will be equals to E into 4 pi R dash. Here we have taken R dash square you are going to be get. So now we'll calculate the total charge enclosed by the Gaussian surface. So total charge enclosed by Gaussian surface. Total charge enclosed by Gaussian surface. Total charge enclosed by the Gaussian surface, which will be equals to actually volume enclosed by it. Volume enclosed by this Gaussian surface into charge per unit volume. Charge per unit volume. Unit volume we have. So therefore, volume enclosed by the Gaussian surface is equals to 4 by 3 pi r dash cube, and the charge per unit volume we can call it as a rho. Here charge density we can call. So this is rho we have. Rho is nothing but the total charge by the volume actually. So now a charge q is uniformly distributed over a sphere of radius capital R we have. So hence rho is equals to charge is enclosed across charge is enclosed, otherwise the charge is distributed, we can say that uniformly distributed over a sphere of how much radius capital R we have. So therefore rho is nothing but it is a total charge by volume. Total volume. So the total charge, we said that it is a Q. Already we have seen plus Q. Here it is there, plus Q. So that Q by the volume enclosed by that is a 4 by 3 pi R, capital R Q. So which we can get it as a 3Q by 4 pi R cube we are going to get. Now if you solve this one, so charge enclosed to the Gaussian surface. Okay. Charge enclosed, charge enclosed in Gaussian surface. Charge enclosed in the Gaussian surface is equals to, it is 4 by 3 pi small r dash cube into that rho value which we have got here as 3q by 4 pi capital R cube we have. So this, if you calculate, we get, if you solve this one, we get it as a q r dash by r whole cube. You are going to get charge enclosed by this Gaussian surface. You are going to get it as what? Q into r dash by r whole cube. Here 3 will get cancels, 4 all this 4 get cancels here, q and as well as this pi you are going to get cancels. The remaining is q into r dash by capital R whole cube we have. So this is the charge enclosed by the Gaussian surface, the point P where it is lying inside of the this Gaussian surface we have, right? So now again from the Gauss law, already we have studied from Gauss law, which is equals to Gauss law, what we have, the charge enclosed by the surface is equals to 1 by epsilon naught times the total charge you are going to be have. That is a charge, not charge, the flux will be equals to the 1 by epsilon naught times the total charge. So here the flux is, we have got it as a E into 4 pi small r dash square, which will be equals to 1 by epsilon naught times the total charge. The total charge we have got it as a q into r dash by r whole cube we have. So now from this we can calculate E is equals to, we get it as a 4 pi epsilon naught into q r dash by r cube will get. Okay, so this is what the total charge enclosed by a point P, which is lying inside of the uniformly charged sphere, inside of the uniformly charged sphere we have. So in the previous case, in the first case, here we have got the charge enclosed by the point P, which is lying outside of the sphere. We have got it as a E is equals to 1 by 4 pi epsilon naught into Q by R square. This is the electric field we have calculated at a point which is located outside of the charged sphere at a distance of small r. Next point, we have calculated the charge at a point on the sphere as we have got as this one, that is equals to E into 1 by 4 pi epsilon naught q by r square we have got. Okay, so this one. And the third case, we have calculated the electric field, a point P which is located inside of the charged sphere P, we have calculated. In that case, we have got the electric field E is equals to 1 by 4 pi epsilon naught into q r dash by r cube. So these are the three different cases when we have calculated the electric field which is located outside of the charged sphere we have calculated, on the charged sphere we have calculated, and similarly which is inside of the charged sphere we have calculated. So this, if you see how picturize this one, how electric field will be there. So here if you take, this is the charge, right? And this is the charge. If you take 1 minute, charged sphere. This is the charged sphere which we have taken, and the center of this charged sphere is O. We have calculated so like this. So this is at the point which is located at the center, and this is of radius r, and this is the radius of r only. So if you see distance which is outside of the sphere, here in this direction, r is the distance if you have. So generally electric field at the center, it will be 0. So as you are moving towards this, what we call onto this surface, the electric field is going to be increases. Then after, as you are moving away from this center, that is outside of the sphere, the electric field value is going to be decreases. That means here in this case, E is directly proportional to R. So here in this case, E is directly proportional to 1 by R square you are going to be have. So the electric field outside of the sphere is inversely proportional to the square of the distance. It is maximum on the surface of the sphere. So at this point, it is maximum at this point or at this point, it is maximum on the surface of the sphere. And if you consider a point P, which is located like inside of the sphere, okay, if you consider P within the electric field will be zero because the entire charge will be resided over the outer surface. So this is what the application, one of the application for this what we call Gauss law, which we have. Okay. So now next after this, we'll move to what is electric potential and what is the potential difference. All these things we'll see here. So next topic will be electric potential. So application, whatever we have seen now, so it is very important. So surely if you see in the examination, you may get either they may ask to prove the Gauss law, otherwise they may ask application. So which we have seen, one of the application. Okay, this is the application you should learn because they in the examination, surely from among these two, you'll get one question. Okay, so next one we'll see about electric potential. Okay, electric potential. So what is electric potential and what is potential difference? All this here will go through here. Okay. So we know that liquids, if you consider, they'll be flowing from higher level to lower level. So the level difference decides the direction of the flow of the liquid. That means always if you take any liquid, it will be flowing from higher level to lower level. So that means the level difference will decides the direction of the flow of a liquid. So similarly, the concept of electric potential is introduced in electrostatistics, like a level of a liquid. So the electric charge flows from a point of higher potential to a point of lower potential always. So it is going to be flow from point of higher potential to point of lower potential. So the electric field around a group of charges can be described by the electric field strength capital E. Okay. So this can also be described by a scalar quantity known as electric potential here. Okay. So electric intensity and electric potential both are related to each other, and it is a matter of convenience which is used to solve a particular problem. So now here we will consider an electric field due to a positive charge Q here. Okay. So here what we'll do is, so we will take a charge here. Okay. So this is the charge Q we have taken. Okay. So this is the charge Q we have taken. So now it will be a positive charge. Test charge always we are going to take a positive charge here. Now we'll, sorry, this is a charge Q we will take here. Now we'll take a positive test charge, a Q naught, which is located within the field. Okay. So here we will take a test charge Q naught, which is located within the field. That means due to this charge Q, so some electric field will be there outside of this one you are going to be have. Now we consider a test charge Q naught within the field we have taken. So now this test charge will experiences an electric repulsive force F due to this one. That means, so here we have this charge Q, which is going to be exhibiting certain electric field here. So due to that, this test charge Q naught is experiencing a force, which is a repulsive force, because these are two are positive charges. Some force is acting on the test charge Q naught due to the test charge plus Q, which is a repulsive here. Suppose this test charge is moved by an external agent, Q naught. Okay, if you are moving this Q naught, charge Q naught, if you are moving by an external agent, say that along this line, from the point, this point to this point. So say that this is a point B, we have, and this is a point A. So what we are doing, this Q naught charge, we are moving from the point B to point A. Suppose if you want to move this test charge Q naught from point B to point A within the electric field, you have to do some work against the force of repulsion, against the force of repulsion. Why? Because this charge Q is exhibiting certain electric field. Within this electric field, this test charge is there. Now we are moving this test charge Q naught against this electric field from point B to point A. Then we have to do some work here. Then we have to do some work. So therefore, the ratio of work done in taking this test charge from one point to other point within the electric field to the magnitude of the test charge is defined as electric potential difference between these points. That means, so here, suppose VA minus VB is the test charge. VA is at one point and VB is another point. So we are moving from which point to point B to point A. So it will be VA minus VB. So this will be the work done again of this charge Q naught. So this is what we call it as a potential difference we are going to be called here. Okay. Suppose if you want to move this charge from within the field from one point to another point, as I told that you have to do some work has to be done. Then the work done here is known as what? Electric potential we are going to be called. Okay, electrical potential is nothing but what? The amount of work done in order to move a charge from a distance, from infinite distance to within the field, a particular point. That is what we call it as a electric potential you are going to be called here. Okay, electric potential. So this is what the definition of the electric potential. Electric potential at a point can be defined as, and that means within the electric field is defined as the work done by an external agent in carrying a unit positive charge from infinite to that point against this electric force is known as what? Electric potential we are going to be called here. Suppose if you take a charge, so around that charge, this electric field of lines of force are what we call distributed. That is what, if you see here, if you take this charge here, okay, so around this one, in all directions like this, like this. So in all directions, is distributed. So this is what we call it as equipotential surface we are going to call here. So this equipotential surface within an electric field is nothing but it is a surface on which the potential is same at every point. So, in other words, we can say that the locus of all points which have the same electric potential is called as electric potential surface we are going to be called here. Okay. So the lines of force at every point of the equipotential surface are perpendicular to the surface you are going to be have here as shown in the figure. So in all directions, they are going to be in the normal to that point you are going to be have in all directions like this. Okay, this is what we have, a equipotential surface you are going to be have. So you can remember some points from this equipotential surface. That is the electric field along the equipotential surface is zero. Electric field along the equipotential surface is zero. And the electric field is always normal to the surface, that is perpendicular. And the work done in moving a charge on the equipotential surface is zero because work is nothing but so the potential difference in the equipotential surface is zero. So therefore, zero into some charge will be equals to zero. And similarly, when the charge is infinite, the equipotential surface is plane you have. So these are the points, some points you have to remember about this equipotential surface. And next, we'll calculate the potential due to this what we call a point charge here. Okay. Now we'll calculate the potential potential due to a point charge. Potential due to a point charge. Here we'll calculate. Okay. So we consider a point charge Q. We'll consider here. Its electric field due to the charge will be, we will take it as a E, which is generally, as we have seen, going outward, as it is a positive charge. So here point charge we'll consider initially. So see here, 1 minute. So this one is a point charge we have been considered here. Okay. So this point charge, whichever we have considered, is a plus Q. So as it is a positive charge, the electric lines of force will be always away from this, are going to be have. Okay. Away from this electric lines of force. Already we have seen the last class how the electric lines of force will be there. That is what we have seen. So these always away from this electric lines of force are going to be have. Okay. So this is away from the charge here. Point charge we have to calculate. Otherwise, we have to calculate the potential at a point B, which is situated at certain distance. At a certain distance, we have to calculate here, right? So here we will take a point here, point B. Okay, point B here we have taken. So this is the point B we have. Okay. So now, which is situated at a distance of, say that RB from here to here. Okay, RB we will take here. Okay, we have considered a point B where we have to calculate the potential, which is situated at a distance of small RB from the charge Q we will take here. Now, we'll select 2 points A and B here. We'll select. So along this radial line, okay. So already we have selected this point B. We have selected, and along this same radial line, 1 minute. I'll draw this. So this is the point B we considered here. I'll draw here point B. Right. Along this radial line, we consider another point A here along this. So we have taken a point B, which is at a distance of RB, and we have taken a point A, which is located along this radial line we taken. Take a test towards this point B. So we'll consider a test charge Q naught, which is right. We'll take a test charge Q naught we have taken, which has to be moved from this point A to the point B. So this test charge has to move from this point A to point B. So suppose if this test charge, if you want to move from the point A to point B, then what we have to do is we have to do some work against the force. That means we have to exert some force by the field on the charge Q, okay, towards uh, the charge Q on the test charge Q naught. Okay, so that force, that means actually we have to move the test charge from the point A to B. So then the force we have to exert on that one, that force actually we will be given by, already we have seen force is given by QE. So in this case, that force F is equals to Q naught E. The force is Q naught E you are going to be have. And moreover, as we move the test charge Q naught towards B, we have to apply that force which is against the field we have to apply, so that this force which we are applying is against the force, so it will be equals to minus Q naught E. Okay, actually the force which we want to exert on the test charge Q naught is QE, generally we will call, that is Q naught E we will call, as this force is exhibit means we are applying against the electric field we are applying, so it will be equals to minus Q naught E we have to apply. So the work done by some external agent to move the charge Q naught through a small distance dr here, if you consider. Okay, the distance here we'll take it as a dr distance we have to move. Okay, how much distance? Dr distance we have to move, which is given by work is nothing but W is equals to force into distance we'll call here. So the work done here, we will consider it as a dW, small work done, dW we have to consider. So work done is equals to force into, this force is Q naught E, and the distance, how much it has been moved, dr distance it has been moved. So it will be equals to Q naught E, and this dr which is moving radial means along the same direction it is moving. So dr it will be equals, we can write E Q naught E dot dr, we can write it as a dr cos theta. The angle is here, it is 180 degrees. Why I am writing 180 degrees? It is against the force we are moving, so that it will be equals to minus Q naught E dr. Why? Because cos 180 is nothing but it will be equals to 1 cos 90 plus 90. So it is sin 90, and we are, which will be equals to minus Q naught E dr. So work done the some external agent in order to move the test charge Q naught from point A to B is given by minus Q naught E dot dr it is given. And this electric field already we have like a this since dw is equals to minus 1 by 4 pi epsilon naught into q naught by r square into dr. Simply we are substituting here in this dw. So it will be e value is 1 by 4 by epsilon naught q by r square we have written in place of E, we have written that one. The remaining will be minus Q naught dr. So that is what we have written, Q naught dr. So dw is equals to minus 1 by 4 pi epsilon naught Q into Q naught by r square into dr. Now, suppose the total work done in order to move the test charge from the point A to B is given by W A B, we can write. So which will be equals to surf integral from the point A to B it has to move. And we have got already dw. A to that Q. So therefore RA is nothing but it is the distance of point A to B. So therefore, if you integrate and if you substitute the limits, Q naught is constant, 4 pi epsilon naught is constant. So it is minus 1 by R. The integration of minus 1 by R square is equals to minus 1 by R becomes. So the limits are from RA to RB. If you substitute these, you'll be getting it as a it will be getting it as a Q by Q into Q naught by 4 pi epsilon naught into one is 1 by RB, another one is 1 by RA. Okay, RA. So therefore, the potential here, the potential difference between the 2 points is given by VB minus VA, which is equals to WAB by Q naught. Okay, so which is equals to Q by 4 pi epsilon naught. Already we have written this one by RB minus 1 by RA. Okay, so this is the work done in order to move a charge from one point to another point, that is VB point A to point B. VB minus VA is equals to, we are getting it as a Q by 4 pi epsilon naught 1 by RB minus 1 by RA. Suppose if you want to find out the potential at a particular point B, the reference point is taken as infinite. So therefore, reference point A, if you take infinite, so the VB value only you are going to get it as a 1 by 4 pi epsilon naught into Q by RB you are going to be get here. So because as you have taken this is A is infinite, so is going is not be there. So 1 by 4 pi epsilon naught q by rb it will be there. So like this, if you want to calculate generalized formula, V is equals to 1 by 4 pi epsilon naught into q by r. So this is the potential due to a point charge here. Okay. So this is what the potential and potential difference and the potential due to a point charge which we have. Okay. So this is what about we have seen today. What are the things which we have seen is we have seen the application of the Gauss law we have seen. So that is electric field due to uniformly charged sphere. We have calculated at three different places on a charged sphere. That is when the point is located outside of the sphere, we have calculated and we have got E is equals to 1 by 4 pi epsilon naught into q by r square. This is the electric field which we have got outside of the charged sphere we have got. And then after we have calculated this electric field at a point on the sphere we have calculated. On the sphere we have got it as a 1 by 4 by epsilon naught q by capital R square Newton Coulomb. This is what we have got. Next we have calculated the potential at a point which is inside of the charged sphere. We have calculated so that we have got that potential sorry electric field inside of the charged sphere. We have got it as a q sorry E is equals to 1 by 4 by epsilon naught q into r dash by r cube. Capital R cube. R dash is nothing but the distance of the point P which is located inside of the sphere at a distance of R dash. And R capital R is the radius of the sphere. And we have compared this all these three, that is the electric field at three different points we have compared. At the center, the zero it is going to be half. As we are moving towards the what we call surface of the charged sphere, electric field is going to be increases like E is proportional to R. As up to this on the charged sphere, it is going to be have the maximum value. E value is maximum on the surface of the charged sphere. And again, as you move away from this charged sphere, automatically the electric field is going to be decreases in this manner. E is proportional to 1 by r square. So this is what the application of the Gauss law we have seen. And next we have define this electric potential. Electric potential is nothing but the amount of work done in order to move a unit positive charge from infinite distance to a particular point within the field. We call it as electric potential. And we have calculated this at two different places. That is, we call it as a potential difference. That is the VA minus VB in between the 2 points A and B. So which we have got it as a W by Q naught. So this is the electric potential as well as the electric potential difference which we have calculated. And also we have seen this what we call potential due to a point charge we have seen. So this is the potential due to a point charge. Uh, Generally, the what is the potential is nothing but the amount of work done in order to move a positive charge from infinite distance to within the field. So we have taken a unit positive charge Q we have been taken, and we have taken a point B we have taken. So this what we have to do is we have to move this charge within the field against this force we have to move. So when we have to moving against the force will be minus. So that force is given minus Q naught E. Okay. So against the force we have to apply. Sorry, against the field we have to apply. So when we are applying against the field, the force will be given by minus sign. So it will be minus Q naught E. So generally the force is F is equals to EQ. So here the discharge is Q naught and the field is E. So against the field we are applying minus Q naught E we have got. So we have no we have done some small amount of work done dw amount of work done we have done in order to move the charge at a distance of dr. So it will be equals to q naught e into dr. So as this dr is nothing but it is totally that is along the radial line against that we have to move. So the angle between them is 180 degrees. So cos 180 is equals to 1. So it will be dw is equals we have got it as a minus q naught e into dr. So already we know that the electric field already we have defined. E is equals 1 by 4 pi epsilon naught q by r square. So therefore in this if you substitute we have got it as minus 1 by 4 pi epsilon naught q into q naught by r square into dr. This is what dw which we have got. So now if you want to move, if you want to do some work in order to move this test charge from point A to B, so we have to take the line integral from the point A to B, that is the limits in between A and B. So we have substituted and we have done the integration part, and we have got this as Q naught by 4 pi epsilon naught into 1 by RB minus 1 by RA we have got. So this is what electric potential due to a point charge we have got. Okay. So in the next class, we'll see the potential due to potential as well as some electric field due to electric dipole. Okay, due to electric dipole, we can calculate what is the potential you have and what is the electric field. Both we can calculate. So in the next class, we'll see the what is electric dipole and as well as what is the potential due to the dipole and what is the electric field due to the dipole. So these are there in your within the syllabus, and these are very important so that you can you can go through the exam. So today whatever we have seen like application, that is very important question, and as well as this electric potential definition is very important. Okay, so we can in the next class we'll move to that one. Okay, right.
Thank
So
you, sir.
okay.